Welcome back to the Brainwave. Today we're talking about matter and energy. If you remember where we left off last time, we were talking about what is matter, what is an atom, and how do we start to classify matter. And that's where we're going to pick up today. We're going to finish classifying matter, we're going to talk about energy and heat in reactions, and then we're going to figure out how can we actually study these things when we're talking about chemicals and elements that we cannot see with our own eyes. Alright, so classifying matter. What is an atom? Well, you should already know that an atom is basically just the smallest unit of matter. And it's made up of what we call a nucleus and then an electron cloud or the electron orbitals. Now the nucleus over here on the right is made up of protons and neutrons. And this is where the majority of the mass of an atom is. And then outside of the nucleus we have what we call the electron orbitals, and these electron orbitals contain the electrons. The electrons are negatively charged, the nucleus is positively charged based off of the protons, the neutrons have a neutral charge. And we'll talk about that more in a future lesson. Now, what we were talking about the last time we met was that we classify these different types of matter, these different atoms, in two main groups: pure substances versus mixtures. Okay? And these pure substances are basically elements that contain one kind of atom. So an example would be just copper, or just hydrogen, or just bromine, or just chloride. Those are what we call elements. And these elements can exist as single atoms or as molecules. So an element would just be one atom, a single atom. So I just have one atom of copper or I have one atom of chloride, whereas a molecule would be having multiple atoms. So for example, instead of having just nitrogen, I would have N2, or oxygen, pure oxygen is O2. So I have two oxygen atoms. Now some of these elements have more than one form. These are what we call allotropes. So an example would be oxygen is O2. That would be pure oxygen that you and I need to breathe. But ozone is O3. And the different structure of O2 versus O3 has very different properties. So for example, O2 is necessary for you and I to stay alive. O3 is a dangerous, deadly gas with a light blue tint that would literally kill you if you breathed it in for too long. And the properties of these allotropic elements depend on what form you find them in and how they exist out in the real world. So some substances are actually made up of more than one kind of atom, and we call these compounds. So an example would be like H2O. This is one hydrogen bonded with two oxygens. Now these compounds are made of atoms that are in a specific arrangement, and the specific arrangement gives them properties and definite composition. However, because this is still two atoms of oxygen bonded with one atom of hydrogen, these are a compound and not a mixture because they maintain their own properties. They're simply bonded together with energy. Now, this is different from a mixture because a mixture contains two or more pure substances, and they have composition and properties that vary. So let's think of a couple of examples. Your food, the food you eat every day. Let's say for breakfast you have a breakfast burrito, and that breakfast burrito consists of a tortilla and some eggs and some cheese and maybe some salsa or onions or potatoes. That is a mixture of food put together into one item that you would call a breakfast burrito. Another good example in the chemical world would be air. That air around you isn't pure oxygen. It contains oxygen, nitrogen, chlorine, ozone, methane. It contains a bunch of different atoms or elements that are mixed together to produce what we commonly just call air. So the idea that I go back to all the time is sweet tea. I can have a cup of tea and I take a little bit of sugar here and I just pour a little bit of sugar in and it immediately dissolves. Okay, so I've got slightly sweet tea or a little sweet tea here. But I can also take this cup of sugar and just dump the entire cup in. Now I have really sweet tea. And that tea is going to absorb the sugar or dissolve that sugar and bring it into a mixture up to a certain point, at which point we call it saturated in solution. And that means that I've now created a saturated mixture of those two compounds, the sugar and the tea. And then once it becomes saturated, the rest of that sugar just sits at the bottom. So this would be an example of a mixture. Now within mixtures, we have two types of mixtures. We have homogeneous or homogeneous mixtures, and then we also have heterogeneous mixtures. Homogeneous mixtures are mixtures where the pure substances that were added together and mixed with each other are distributed uniformly. So an example would be sweet tea, or like syrup or air, where we can't really tell that they're separated in any way, whereas a heterogeneous mixture are substances that aren't evenly distributed. So this would be something like mixing water and sand. If you put sand in water, the sand just sinks to the bottom and forms its own layer. Or oil and water. If I mix oil and water, they have different properties, and so they never will truly mix. They basically separate out based on their density. And we can work with these mixtures. So if we put something into a mixture, we don't have to leave it as a mixture. There are ways to get it out. And we can do this using filtration, distillation, or evaporation. And all of these techniques rely on knowing the different pure substances, particle sizes, as well as their boiling points. All right, so that's the end of how can we classify matter. Now let's talk about what it takes to actually do reactions and to process chemicals. Let's think of it in that sense. And that is energy and heat. So energy is an extremely broad concept. Okay, but to put it simply, energy is just the capacity to do work. So if I am sitting here but my hands are moving, I am doing work. My body's burning calories and I have the capacity to do work. Okay, if I run from here, from point A to point B, I am doing work. I am expending energy. Okay, so energy can be anything that has the capacity to do work, and this can involve changes that are either physical or chemical. And when we're specifically talking about changes in matter, this involves changes in energy. So let's think about the water example from the lab that we did. We took water and we basically let it melt. So we took ice, we melted the ice, then we boiled the liquid water, and then we allowed it to evaporate and turn into a gas. So we went through stages or changes in the states of matter of that compound, water, and so we went from solid to liquid to gas. Okay, and we have different names for these changes in states of matter. So for example, going from solid to liquid is melting, and going from liquid to solid is freezing. So if you put water in a ice tray and put it in your freezer, you are freezing that water and turning it into a solid. If we go from liquid to gas, that's evaporation. If we go from gas to liquid, that's condensation. If we go from gas to a solid, that's deposition. That hardly ever happens for most compounds, or most elements, we'll say. If we go from solid to gas, that's sublimation. All right, so these changes in matter have different energy requirements to cause that change in matter. So they either have to release energy or take energy in to do that change in matter, and they each have a unique name. And this amount of energy that is required to go through that change in matter has a specific name, and we call those endothermic or exothermic processes, or endothermic or exothermic reactions. Okay, so an endothermic reaction is a reaction that requires energy to change that matter. So energy is being absorbed. Endo, inside. So think about that as the reaction has to take in energy to change that matter. Whereas exo is exiting, it is outside of the reaction. So exothermic is releasing heat or energy during the reaction. So let's look at these charts on the bottom right here. So the one on the left that says endothermic reaction. On the y-axis we have the amount of energy. On the x-axis we have basically the time or where they are in the reaction. So in the beginning we're going to start with two elements. We're going to have A plus B. And we add A and B together, and we see that we have an increase in the amount of energy in the reaction, and then it reaches a peak and it drops off slightly, and we end up with a product that we're calling C. So in this case, the end reaction, or excuse me, the end product has a higher amount of energy than the initial two reactants. So that took energy. It had to take in energy or absorb energy to produce that new product. Whereas an exothermic reaction is the opposite. So in an exothermic reaction, we have two reactants, A and B, and they start at a higher energy. Initially, they're going to take in a little bit of energy, but they reach a peak, and then at that point, they start to release energy as heat, or likely they release energy as heat, and the end product has a lower total energy than the initial two reactants, A and B. So that's an endothermic versus an exothermic reaction, and we have to understand this so that we can understand what's happening when we change the states of matter or when we go through chemical reactions for different elements. Now we're talking about energy leaving a reaction potentially as heat, or energy being transferred from the environment inside of a reaction. So a reaction would be taking in energy from the environment. So the question here is, are we creating that energy, or what happens to it? And what we know from just science generally and from other researchers is that there is a fundamental law of the universe, and we call this the law of conservation of energy. And this is actually the first law of thermodynamics. So it states that energy cannot be created or destroyed, it's simply transformed. Okay, so in chemistry, we talk about how energy is being transferred or transformed out of a reaction through an exothermic process or into a reaction in an endothermic process from the environment or from another chemical in that reaction. So for example, let's just use water. Let's say that I take ice and I want to go from ice, a solid form, into a gaseous form. Okay, so that ice is cold and it contains a low amount of energy relative to a gaseous molecule or a gaseous compound where the atoms are going to be moving really quickly. So in order to get it from a solid into a gaseous form, I'm going to have to heat a beaker of water to turn it from solid to gas. Okay, so I'm going to have to add heat to that reaction from my environment, which means that that is now an endothermic reaction. It requires energy to be absorbed by the water to turn it from a solid, or to change the state of matter from a solid to a gas, telling me that is an endothermic reaction. It has to absorb that. Now I'm not creating that energy from thin air. I can get that energy from something like a hot plate, which uses electricity to convert that to heat to then transfer to my beaker, or I could also use a Bunsen burner, which would take propane or some kind of natural gas and burn it to create heat. Right? And then we would transfer that energy. So that is an example of the conservation of energy. We are absorbing energy from our environment or from an external source to then transfer into our chemical reaction or our state of matter change to move that from a solid form into a gaseous form. Now what's really interesting about this transfer of energy during chemical reactions or during physical exchanges of energy is that this energy is transferred between objects that are technically at different temperatures. So energy is either being released or absorbed as heat in many situations. But heat is not the same as temperature. So temperature is a measure of how hot or cold something is, whereas heat is the measure of the average kinetic energy of a particle. So heat is a measure of how quickly something is moving on average in that substance or in that chemical or in that element, whatever you want to think of it as, whereas temperature is the measurement of that average speed or of that average kinetic energy. So heat and temperature are different. And this is very important to understand because we're going to spend quite a bit of time talking about temperature in this class. And we're going to use that as a way to understand the movement of these particles and how the reactions that we're talking about are being affected at different points in time. And typically in the United States, we talk about temperature in Fahrenheit, okay, but we will not be doing that in this course. We will be talking about it either as Celsius or as Kelvin. Kelvin is technically the official SI unit of temperature. It's a measure, an absolute temperature for the entire universe, but more convenient would be to use the Celsius, so we likely will talk about Celsius also. And what's really interesting about this temperature, this measure of how hot or cold something is that the transfer of heat does not always mean that we have a change in the temperature. Okay, so let me explain that a little bit. So let's say I have water. Let's look at this diagram on the right here. On the x-axis, we have the amount of heat that's being added. On the y-axis, we have the temperature change. Okay, so let's say we have water in a beaker, and this water is starting as a solid. This would be ice. Okay, so I'm going to start this water, and I'm going to start to heat it. Eventually, we reach 0 degrees Celsius. This is what we would consider to be the melting point of the water. So the water is basically at a point where it is starting to turn into a liquid form, but it is not all liquid. And at this point, we're going to have a point where basically the water stays a constant temperature. We're not seeing any change in the temperature. The reason for this is that not all of the particles have reached the same average kinetic energy. So some particles are moving a little bit slower than others, and others are already moving a little bit faster because they're already in a liquid state. Okay, so we have this plateau at about 0 degrees Celsius. And then eventually all of the particles reach the same average kinetic energy. And at that point, the temperature begins to rise again, and the heat also is rising at the same time. And at this point, water is being heated as a liquid. Once the water has been heated as a liquid, we now reach the boiling point, or the point of vaporization of that liquid. And again, we get a point of stagnation where the temperature is not changing, but the amount of heat that is being added to the substance or to the compound is still increasing. So we see again here at about 100 degrees Celsius, the boiling point of water, we see that the temperature stays the same, and that's because the majority of the particles there are moving at different speeds. So we have some that are still moving with the kinetic energy of a liquid, and we have some that have the kinetic energy of a gas. So we need to add more heat to that compound to move the entire average kinetic energy of the compound past the boiling point or past the temperature of vaporization. And at that point, we turn that water from a liquid into a gas. At that point, once it turns into a gas and it has that average kinetic energy of a gas, we start to see that the temperature climbs again. So this is why transfer of heat won't always affect the temperature of a compound or of a substance. Now, one of the ways that we can more specifically measure this amount of heat that it takes to change a unit of mass of a material is what we call specific heat, and that is the definition of specific heat: the quantity of heat required to raise a unit of mass by 1 degree Celsius or 1 degree Kelvin, and we assume we have constant pressure and volume. So let's think of this as a simple example. So in lab, what we did was we made what we call a coffee cup calorimeter. Basically, we took a styrofoam cup, okay, we put an amount of water in it, and we measured the mass of that water, and then we also took the temperature of that water. And then we took a boiling beaker of water and we dropped a piece of metal in it, okay, and we boiled that piece of metal for a set amount of time, and then we moved the metal from the beaker into the cold cup, the cold styrofoam cup, and we measured the amount of temperature change of that water in the styrofoam cup. And by doing this, what we were able to do is calculate the amount of heat that was transferred from the piece of metal to the water that was in the styrofoam cup, allowing us to calculate the specific heat that was required to raise the mass, raise the average kinetic energy of that, aka the heat of that metal, by 1 degree Celsius, which tells us the specific heat. So we're using temperature as a unit to measure the speed or the average movement, how hot or cold that piece of metal was. And then we're using heat as a tool to understand the amount of energy that was required to raise the temperature of that material, so then we can identify what element or compound we had in our beaker initially. Okay, because that's one of the physical properties, is the specific heat. So this is a way that we can use the heat and the temperature together to understand the physical properties and the changes in matter. All right, and lastly, let's talk about the scientific method, because now we're talking about things that we can't see. So how can I measure something that I can't see? Well, really the answer is a story as old as time. People have always been curious about the natural world. We have records as far back as ancient Greece, where they had early scientists that had ideas about chemistry. So we created what we call the scientific method. And there are 5 basic steps to the scientific method. We have an observation or we form a question that leads us to building a hypothesis or forming a hypothesis. We then test that hypothesis, we analyze our data, we report our conclusions, and we repeat the cycle. Now, one of the key parts of the scientific method is that the variables must be independent. I can't say this is my left hand and it is tied to my right hand, but my right hand moves on its own. And I know that's a silly example, but what I'm saying is you can't have two things that are attached at the hip and pretend that they're operating independently. This thing has to be completely different than this thing, and you have to be able to measure them independently of each other. They cannot be connected in any way or dependent on each other in any way. Now, within the scientific method, we have some key terms that we have created over time. So, for example, we have a theory. So, you've probably heard of the theory of gravity. Okay, the theory of gravity is basically a hypothesis that has been tested for almost 100 years now. And it's not always exactly right, but 99.99% of the time it withstands the test that we put it up against. There may be one exception or two exceptions. Okay, a law is even stronger than a theory. So a theory is like, I formed a hypothesis, I have tested it hundreds if not thousands of times, and 99.99% of the time it is correct. Whereas a law is a statement that is reliable in describing the natural world. Just period, flat out, it always will be true. Okay, that's how we need to think of it. Is a law is always true. Just like a law in a civilization, if you break a law, there's a major penalty for that, and that's because you are breaking a described behavior of the world or of the community, and at that point, you will face a punishment. With science, it is, as far as we know, it is impossible to break a law. If we were capable of breaking a law, then that would mean that it is not a law, then it is still a theory. So an example of a law that we've talked about is the law of conservation of mass. So products of a chemical reaction have to have the same mass as the reactant. So let's say I take water and I boil it. At that point, I'm breaking it up and I'm producing hydrogen and oxygen. In theory, the products of that water that I boiled have to have the same mass as the initial water that I started to boil. Now, what we have to remember is that we are adding heat to this reaction, so some of that energy is being added to break those bonds, and then some of that energy is going to be lost to the environment as heat, and there are a ton of examples of that happening over and over again. Alright, that's all I had for you guys today. Hope you have a great day. Thank you for your time, your energy, your effort. I'll see you next time.